We're going to talk about parametric equations. Parametric equations are useful when you're trying to describe the motion of something and it's not a single function, it can be fairly complex. So for example, if we were watching a fly and we were kind of tracing the path of the fly, and at the time we started watching it, it was at a certain XY position, and then when we looked at it later at t equal 1, it had moved to a different x and y position, and then at t equal 2 another xy position, and so forth. And so we are parameterizing the path of this fly in terms of time, so we're using the variable t, and at any given time we can describe where the fly is by giving this x coordinate and y coordinate, so that'll be a function of time. Now let's go ahead and analyze the motion of a particle whose path is described by the parametric equations x equal t squared and y equal t, and t goes from 0 to 1. And we often have that domain restriction on our parameter. So here we're looking between 0 and 1. And then in a minute we'll eliminate the parameter and express the graph in terms of x, y with appropriate restrictions. So first of all, normally we make this t chart, but we're going to have 3 lines because we're going to use t, x, and y. So we're going to choose various t's between 0 and 1, substitute those in to get the corresponding x and y position, and then plot those. So we'll start with 0, and of course 0 squared is 0 and y equals 0. So we plot that xy point 0, 0. Then we'll let t be 0.2, so if we square that we get 0.04, and y is equal to t, so that's still 0.2, and we can plot that point. Then 0.4 squared is 0.16, and our y is still 0.4, and we can plot that point. Then let's do 0.6 squared is 0.36, and 0.6 for the y, plot that point. 0.8 squared is 0.64, our y is 0.8, and we'll plot that xy coordinate, and then we'll put in our upper restriction on our domain 1. 1 squared is 1, and our y is 1, and we plot that point. So we can see how our particle moved between 0 and 1, and we could draw that then into a connecting function there. And one of the things that a parameterized path has that we won't see when we eliminate the parameter is it has an orientation or a direction that it's moving. So as the t increases, we see the direction that the particle moves. Now let's go ahead and eliminate the parameter. So essentially we just want to solve one of these so we can substitute in to eliminate t, but we already have y equal t, so we could just substitute y in right here. So we'd have x equals y squared, which we recognize as a parabola that opens to the right. However, because of our restriction on t just between 0 and 1, we would need to now make a restriction on x. It's only going to go between 0 and 1, but if we did that, we actually would have these negative values as well, so we need to also make a restriction on y. It's also going to only go between 0 and 1. Another way we could do this is we could solve this for y, and we could have y equals square root of x, and we wouldn't put the plus minus because we're not including the negative values there. And so if we did that, then we could just have that restriction of x goes between 0 and 1. So this may be the very best way to do that. Now let's analyze the motion of a particle whose path is described by the parametric equations x equal 2 cosine t, y equal 2 sine t, as t goes between 0 and 2 pi. And actually before we do that, let's go ahead and watch a couple of these in action so we can see why they look like they do. So here we have parameterized in terms of t, x, and y, where x equal cosine t and y equals sine t. For x equals cosine t, we have it plotted here at 0, it's 1, then it goes down here to its intercept, down to its minimum of -1, and back. Now we're actually, when we're going to look at these plotted on an xy plane, we're going to turn this. If you look here, we're going to have our x here and t so that we can see what it's doing as far as in the horizontal direction, which is what x is, because we see it's just going to go from 1 to -1 to 1 like that. And then when we look at our sine t at 0 at 0, then it's going to go to its maximum of 1, then down to its minimum. So we want to combine these two, and so we know that we start out at t equals 0, x is 1, and y is 0. So we're going to start at this point right here. And then as we increase with t, as we move along here, you can see what's happening. The y is increasing, the x is decreasing, and we're tracing out this circular path. When we get to this point right here, we see that our x is 0, and our y is at its maximum of 1, and we're at this point on this circle. As we continue around, we're going to see that y is going to decrease and x is going to go negative and get larger and larger negative till it gets to -1. So as we move around here and we get to this point, we see that we have our y value being 0 and our x value is at -1, and then we see that x's are going to increase to 0 as y's are going to go negative. And here we go around there, and we can see we get to that point when the x is 0 and the y is -1, and then continue around, and as we get back to 2 pi, we are back where we started there. Now we can also look at this with some other functions. Let's look at one where the only thing we changed here is the period of the cosine. So the cosine now has a period of 2 pi over 3. Okay, so as y cycles once, we see x cycles 3 times here, and as we watch this around, then we can see how it traces out this interesting path. Here we go with it. We had the one, then the second time, and then the third time. So following this video, we're going to have links to these so you can go kind of play with them and observe what happens. So now we've seen what some of these do. We see that this cosine t and sine t is going to be circular, but as we put in t equals 0, we get our x is 2 and our y is 0. So the radius is going to be 2 as we do this. We can see that we'd start here, and as we move over here to pi over 2, we would have the x value being 0 and the y value being 2, and so forth as we move around. So it starts here, moves around the circle in this direction. By the time we get to 2 pi, we are back where we started there at the x equals 2, y equals 0. Now, if we want to eliminate the parameter here, this one's going to be a little bit tricky, so let's see how we do that. First, I'm going to square both sides. X squared equal 4 cosine squared t, and I'm going to do the same thing with the y squared equal 4 sine squared t. And then I'm going to solve these for cosine squared and sine squared. So we have x squared over 4 equals cosine squared t, and y squared over 4 equals sine squared t. Now I'm going to substitute these in my favorite trig identity, which is cosine squared t plus sine squared t equals 1. So let's go ahead and do the substitution, and we will have x squared over 4 plus y squared over 4 equal 1. We could multiply everything by 4 so that we could clear this of fractions, and then we could see that we have the recognizable equation of a circle centered at the origin of radius 2. So there we go. The only thing different here is that doesn't show us the direction that the particle traveled, and we lose that when we eliminate the parameter. Now we can get all kinds of fun things. Here's kind of an interesting parameterized in terms of t, x, and y, and as we go from -6 pi to 6 pi, look at our interesting shape here. So following this video, there will be some links where you can go kind of play around with some of these parametric equations.